When the Open Handset Alliance launched the HTC Dream in 2008, they released an open-source operating system meant to run on almost anything. Over the following decade, the platform evolved rapidly. It gained essential features like Google Maps navigation, overhauled its memory management, and in 2014 replaced its entire execution engine with the Android Runtime, or ART. By 2019, the interface had matured into gesture-based controls, and the development team dropped the famous dessert-themed naming conventions for a straightforward numerical system. But beneath those decades of user interface updates, the technical identity of the platform has remained consistent. Android is, at its core, a customized Linux distribution. This creates a strict engineering problem. The operating system has to accommodate thousands of highly varied, unpredictable hardware configurations, different cameras, processors, and sensors, while simultaneously providing a completely uniform and stable environment for software developers to write their code. To maintain order, the OS takes on three rigid responsibilities. It manages the physical hardware, it provides background services like security and networking, and it executes applications. Because the hardware ecosystem is fragmented, developers cannot write applications as massive, monolithic blocks of code. If one piece of hardware fails or differs, a monolithic app crashes entirely. Instead, Android applications are built as highly modular components. This means the development process shifts from writing a single continuous program to managing communication between these distinct layered modules. To build for Android, you have to learn how isolated components talk to one another across a strictly structured architectural stack. To see exactly where those applications live, we have to map the software architecture from the bottom up. This block diagram shows the complete logical architecture of the Android platform, organizing everything from the physical device up to the user's screen. The lowest level of the stack is the Linux kernel. This is the only layer that interacts with the raw physical device. It handles all the low-level hardware drivers, memory management, and power states. Sitting directly on top of the kernel is the middle tier, system libraries, and the Android Runtime. The Android Runtime serves as the execution engine. It takes the high-level code written by a developer and efficiently translates it down into the specific machine code that the Linux kernel requires for that exact physical device. Above the runtime sits the application framework. This tier acts as a protective buffer. It provides the application programming interfaces, the APIs, that developers actually write their code against. It effectively shields them from ever having to interact directly with the Linux kernel. This specific layered abstraction is what allows a single piece of application code to run securely on thousands of different hardware configurations without requiring unique modifications for every device. When we move past the framework and look at the toppest layer of the stack, we find the applications themselves. A compiled Android app is never a single file. By design, it requires three specific, separate structural pieces to function. The first is the activity class. This is written in Java or Kotlin, and it contains the programmatic logic for a single screen that the user directly interacts with. The second piece is the layout file, written in XML. This dictates the actual visual structure of that screen, where the text boxes, buttons, and labels go. The third piece is the Android manifest file. The manifest acts as the app's instruction manual for the operating system. Before the app can run, the OS reads this file to check what hardware permissions are required, what external libraries are needed, and which specific activity should load first. The UI design is locked in the XML. The logic is locked in the activity. The system configurations are locked in the manifest. By separating these concerns, Android ensures that apps remain modular and easier for the system to manage. That modularity extends to the broader capabilities of the app. Every Android application is constructed from four core building blocks: activities, services, broadcast receivers, and content providers. While activities handle the user interface, services execute heavy logic behind the scenes. They process tasks like downloading files or playing audio without freezing the screen the user is looking at. But because of Android's strict security model, these four components are completely isolated from one another. They cannot contradict each other's code. To bridge these nodes, the OS requires developers to use a universal messaging object called an intent. An explicit intent is used when you know exactly which component needs to respond. You specify the target by its exact class name. If a user taps a button on your app's main screen and you want to load the login screen, you send an explicit intent internally from the main activity to the login activity. Conversely, an implicit intent does not name a specific target. Instead, it declares a general action that needs to be performed. If your app needs to show coordinates on a map, you broadcast an implicit intent to the OS. The framework then searches for any external application on the device capable of rendering a map and hands the coordinates off to it. By mandating that all communication pass through these intent objects, the OS ensures that no component can bypass the system's security framework or trigger unauthorized actions in another application. When you tap an application icon on your home screen, the entire stack activates in a fraction of a second. The hardware registers the physical touch, and the OS instantly generates a starting intent object. The application framework intercepts that intent, cross-referencing the app's manifest file to verify that the target activity has the correct permissions approved by the kernel. Once verified, the target activity class is executed within the Android Runtime environment. Finally, the activity parses its associated layout XML file, pushing the structural wireframes up through the stack to render the user interface on the glass. This layered separation of concerns is what enables the system to handle thousands of hardware variations while keeping each application's logic securely isolated. By abstracting the hardware, compartmentalizing the code, and routing all actions through intents, developers can build software that scales across a global, fragmented ecosystem with confidence.